The deep ocean is a vast and mysterious world where pressures are so intense that they would crush a human body in seconds. Yet, life thrives in these extreme depths, where fish and other creatures not only survive but flourish. So how do deep-sea fish manage to withstand the crushing pressure of the deep ocean? What adaptations have they evolved to endure an environment that would be inhospitable to most life forms? In this video, we'll dive deep into the fascinating ways these fish survive against all odds. To truly understand how deep-sea fish survive, it's crucial to first grasp the nature of the pressure they endure. The pressure in the ocean increases with depth. For every 10 meters you descend, the pressure increases by about 1 atmosphere ATM. At 1,000 meters below the surface, the pressure is over 100 times greater than what we experience at sea level. But the pressure doesn't stop increasing there. At the deepest point on Earth, the Mariana Trench, which lies about 11,000 meters below sea level, the pressure is a staggering 1,000 times the pressure we feel at the surface. This crushing pressure is one of the most extreme forces in nature. In the deep ocean, the pressure is so intense that it can crush a human body or a submarine in seconds. The problem for most organisms is that the air-filled spaces in their bodies, such as lungs or swim bladders, become vulnerable. These spaces cannot withstand the immense weight of the water pressing down from above. For most surface-dwelling fish, having an air-filled swim bladder is crucial for buoyancy, but at extreme depths, it would collapse under the pressure. This is where deep-sea fish have evolved remarkable adaptations to survive. One of the key adaptations that deep-sea fish have developed is the absence of air-filled spaces in their bodies. At the surface, most fish rely on a swim bladder gas-filled sac inside their bodies to regulate their buoyancy. This swim bladder allows fish to float at a specific depth. However, at depths where pressure is far too intense, this air-filled organ would be crushed, rendering it useless. Deep-sea fish, therefore, lack swim bladders altogether. Instead, they have evolved other methods of maintaining buoyancy. Instead of relying on air, deep-sea fish use oil-filled sacs or gelatinous tissues to stay buoyant. The oils in their bodies are denser than the gases typically used in swim bladders, providing a buoyancy mechanism that is not susceptible to the crushing pressure of the deep ocean. These oils have a high lipid content, which allows the fish to maintain their position in the water column without the risk of their buoyancy system collapsing under pressure. Some fish have even evolved gelatinous bodies, which are not only less dense but also flexible, allowing them to bend and compress under pressure without harm. The structure of deep-sea fish bones is another key factor that helps them survive extreme pressure. While most fish have hard, calcified bones, deep-sea fish have bones that are either cartilaginous like the cartilage in our ears and nose or soft and flexible. This allows their skeletons to bend and adapt to the pressure rather than cracking or shattering. Cartilage is far more resilient to pressure than bone, and this allows deep-sea fish to maintain their structural integrity in an environment that would crush most other organisms. But the true biochemical magic of deep-sea fish lies in their protein structures. At extreme depths, proteins, the building blocks of all living organisms, are at risk of denaturing, falling apart due to the high-pressure environment. Denaturation occurs when proteins lose their shape and, as a result, stop functioning properly. For deep-sea fish, this would be a deadly problem. To counteract this, deep-sea fish have evolved piezolites, special molecules that help stabilize proteins and prevent them from breaking down under high pressure. One well-known piezolite in deep-sea fish is TMAO trimethylamine anoxide, which plays a crucial role in stabilizing proteins and ensuring that the fish's cells continue to function properly despite the extreme conditions. These biochemical adaptations help deep-sea fish maintain cellular integrity and continue functioning in an environment that would destroy most other life forms. The evolutionary journey of deep-sea fish is a fascinating one. Over millions of years, these creatures have adapted to the extreme conditions of the deep ocean, where pressure, temperature, and lack of light create one of the harshest environments on Earth. One of the most well-known deep-sea creatures is the Mariana snailfish, which has been found at depths of over 1,000 meters, holding the record as the deepest living vertebrate. Its body is so finely adapted to high-pressure environments that it cannot survive if brought to the surface too quickly. Its gelatinous, flexible structure is perfect for withstanding the crushing forces of the deep, and its cellular chemistry is perfectly suited to handle the extreme conditions. The anglerfish, another deep-sea dweller, is also a master of survival. Known for its glowing lure, the anglerfish uses bioluminescence to attract prey in the total darkness of the deep ocean. But this glow is just one part of its survival toolkit. The anglerfish's soft, flexible body is perfectly adapted to cope with the immense pressure of the deep ocean. In addition, its bioluminescent organs, which emit light through chemical reactions in special cells, provide a critical advantage for both hunting and mating in an environment where sunlight doesn't reach. The study of these incredible fish isn't just fascinating, it also has real-world applications. By understanding how deep-sea creatures survive such extreme pressure, scientists can develop new technologies inspired by these natural adaptations. Biomimicry, or the design and production of materials inspired by natural organisms, is one area where deep-sea research is already making an impact. For example, the materials that deep-sea fish use to withstand pressure could inspire pressure-resistant materials used in underwater exploration or even in space travel, where pressure is a critical factor. Additionally, understanding the unique biochemistry of deep-sea fish could lead to advances in medicine, particularly in developing new enzymes or drugs that function in extreme environments, or in creating more durable materials for use in high-pressure industries like deep-sea mining. Furthermore, the deep-sea environment is an area of growing interest in the fields of conservation and sustainable development. As we learn more about the unique ecosystems of the deep ocean, it becomes clearer that these environments are fragile and potentially threatened by human activities. By studying how deep-sea fish survive, we gain valuable insights into the health of the deep-sea ecosystem and the need to protect it from the harmful effects of climate change, overfishing, and deep-sea mining. In conclusion, the deep sea is an incredibly harsh environment, but deep-sea fish have evolved extraordinary adaptations to survive in this pressure-packed world. From their gelatinous bodies and flexible bones to their specialized biochemical makeup, these fish are truly marvels of evolution. By studying them, we not only gain a greater understanding of life in extreme conditions, but also unlock new possibilities for technology, medicine, and conservation. The deep sea may be dark, cold, and crushing, but it is also a testament to the resilience and ingenuity of life on Earth.